Okay, so last time we were in chapter 8, so we got a little bit more to go on that, but we were talking about really different types of formulas, empirical formulas, molecular formulas, and we talked about how to sort of calculate your empirical formula. So a couple of the steps as we talked about, remember that if you're given everybody in percent composition, you basically want to get them to grams or whatever unit you may be given. You do want to get everybody to grams. If it is percent composition by mass, you do want to make sure that the percentages do add up to 100%, that you're not missing any element. Then what we typically would do is just assume that we have 100 grams. Again, the reason we assume we have 100 grams is it pretty much keeps the percentages numbers and the grams numbers the same. Once we have them in grams, we then convert our grams to moles. And that's using our molar mass from the periodic table, which is in grams per mole here. And at that point, we will have basically the moles of each of the elements that are present. We always then divide by the smallest number of moles. So you're going to take each element's moles, divide by the smallest. And if you hit all whole numbers at that point, that pretty much will be your empirical formula. Remember that we try not to round too much on these unless it's really, really close to kind of the whole number, like 1.98, 2.03, something like that, but really, really close to it. If we do not hit all whole numbers, so for example, like we got something like this, we do need to figure out a factor to multiply that number by, again, to get it to a whole number. In this case, we would multiply it by 2. And that would give us A3B2 in this case. And that would be our proper empirical formula. So typically common endings of numbers like 0.33, 0.50, those type of endings, again, are too far to round. You do need to basically come up with a factor to multiply the empirical formula by to get to whole numbers. Any questions on that there? All right, so I think we left off on this example, so let's do a few more here. The composition of this acid is 49.3% carbon, 6.9% hydrogen, and 43.8% oxygen. What is the empirical formula? Again, carbon is 12.01, hydrogen 1.008, oxygen 16. Okay, let's take a look, see how you're doing. Once again, when you do have percentages, as I mentioned, kind of take a quick look, and it's about 100%. So again, we're not missing any sort of elements. In this case, we could assume 100 grams, and once again, we're assuming that 100 grams just to keep the numbers the same. That means that we would essentially have 49.3 grams of carbon, 6.9 grams of hydrogen, and 43.8 grams of oxygen. Using the molar mass from the periodic table here for each of those elements, we're going to convert them into moles. So our 1.008 here for our hydrogen and our oxygen 16. So in this case here, 49.3 divided by 12.01, gonna get us a 4.1049. 6.9 divided by 1.008, 6.8452. And lastly here, 43.8 divided by 16. Going to give us a 2.7375 moles of oxygen. Again, in this case, we are going to divide by the smallest number of moles. And in this case, it does look like it is the oxygen. So we're going to take everybody and divide it by the oxygen here. That gives us a 1 there. We will have 6.8452. Looks like a 2.5 there, and a 1.5 there. So in this case, we will end up with an empirical formula of C 1.5, H 2.5, and oxygen. Once again, as we talked about, we cannot have these sort of decimals here. So in this case, we actually have 2 that we need to fix. And in this case, one number will fix them both. We could basically multiply everybody by 2 in this case. Should clear that. And that's going to give us a C3H5O2 as the proper empirical formula. As again, that 2 will clear basically both of those problem ones there. Any questions on that there? Okay, so in addition to empirical formula, we could also calculate the molecular formula. And let's talk a little bit about the things that you do need to calculate the molecular formula. And when we look at to calculate the molecular formula, there's really kind of 3 things that you kind of need here to do it. You need the approximate molar mass of the compound. In textbook problems, those are usually given to you. So somewhere in the problem, they'll tell you that the molar mass of this compound is this number. It may also give you a range, for example. It may say, hey, it ranges from like 100 to 120 grams per mole, something like that. You will need the empirical formula. So either it will be given to you or you need to calculate it yourself. And really the third thing here that you need is the empirical formula's molar mass. So once again, you kind of want to get that empirical formula and then get the molar mass of it. And what you do with really these 2 numbers here, the molar mass of the compound and the empirical formula's molar mass, is you divide it. So you take the molar mass of the compound divided by the empirical formula's molar mass, and that's going to get you a number. And this number is basically the number that you multiply the empirical formula by. And that will get you to your molecular formula. Now, I will say we talked about earlier, when you're doing sort of the empirical formula, you don't want to really round unless it's really, really close to the whole number. I would say in this case, for this calculation, you could be a little bit more generous in your rounding. It should really be a whole number multiple of the empirical formula. So you could kind of round a little bit more than you maybe normally would and do an empirical formula. So for example, if we did this and we got a 3 and we had our, say, empirical formula here, we basically would just multiply that by 3, and that would give us something in this example here of this, and that would be your molecular formula. Sometimes people will write it in books, and I'm not a big fan of it, but sometimes people will put the empirical formula in parentheses and put the little number down here. I think you should just distribute it and sort of end up with a formula like that. But you will sometimes see people sort of do that, kind of put the empirical formula in parentheses and a little number next to it. But I would recommend just distributing it out so you get, bless you, the molecular formula. Any questions on that there? All right, so let's try one here. Empirical formula of acetic acid, CH2O. What is the molecular formula? And again, okay, so let's take a look at this one. Again, we're looking for the molecular formula. And we really need, again, 3 things. We need the molar mass of the compound, which again is typically given to you. So that is what the 60 there is. We need the empirical formula, which in this case was given to us, so we don't have to calculate it ourselves. And the third thing that we need is the molar mass of the empirical formula that we do need to calculate here. So our empirical formula, there's molar mass would be 12.01 plus 2 times 1.008 for our hydrogens and a 16 there for our oxygens. Going to give us about a 30.03 grams per mole. So now that we have basically both molar masses that we need, we're going to take the molar mass of the compound. We're going to divide it by the molar mass of the empirical formula. And that'll give us approximately, in this case, about a 2. 1.99 something, I think. That 2 is again basically the factor by which we're going to multiply our empirical formula by, which will give us a C2H4O2 as our molecular formula in this case. Yeah. Any questions on that one there? All right, so let's try another one then and see how we're doing. All right, so a compound contains 1.52 grams of nitrogen, 3.47 grams of oxygen. The molar mass there is between 90 and 95 grams per mole. What is the molecular formula and the molar mass of the compound? Which again is given to us here as a range of numbers. We do need the empirical formula, which we're not given, so we do need to calculate it. And again, we would then afterwards need the molar mass of our empirical formula. So might as well start with our empirical formula here. We have everybody in grams, so we'll start with our converting grams to moles. Using the molar mass for nitrogen of 1401. And for our oxygen there, molar mass of 16 grams per mole. That gets us 1.52 divided by 1401, 0.1085. Do the same thing here for our oxygen, 347 basically divided by 16, 0.2169. Here we're going to divide by the smallest, which does look like it is the nitrogen in this case. And give us a 1 there, and it should be about a 2, I believe. About 1.99 or so, which rounds to about a 2. That's going to give us an empirical formula here of NO2. Any questions up to that point? So that is the second thing that we need. So the last thing we should calculate here again is our molar mass of our empirical formula, so we could use it. And in this case, that would get us 1401 plus basically 32. So 4601 grams per mole. So in this case, we do have a sort of a range of numbers. So if you wanted to, you could have chose sort of the bottom range there. Took the 90 divided by 4601. And if you did sort of the bottom there, it'll give you about a 1.96. You go about halfway between the two numbers at 92.5 grams per mole. Kind of between the upper and lower limit there. And if you did that, 92.5 divided by 4601, about a 201. And if you chose sort of the upper limit, you got about 2.06 here. So you definitely don't have to do all three, just to show you, pretty much no matter where you choose in this range, and they're all pretty much a 2 in this case. Bless you. So bless you. I say most people would probably maybe just go in the middle of the range there. It's just a good probably place to go with in a case like this. So we're going to go with 2 as our number. And again, that is what we're going to multiply our empirical formula by. And that will give us an N2O4 in this case. And if we want the molar mass of this guy, then would be 2 times 1401 plus 4 times 16. And we see that the molar mass of this particular compound will actually be about 9202 grams per mole, which is about in the middle where we chose as one of them. Any questions on how to do that there? So again, if you have a range, you can really choose any number. They all should pretty much hit you the same way. But again, kind of go in the middle is usually a pretty good move. We'll take a look at one more here to finish up this chapter. Phosphorus oxide contains 43.64% phosphorus. 56.36% oxygen, has a molar mass of 283.89. What's the empirical and molecular formula? Phosphorus is 3097, oxygen 16. Quickly take a peek here. And again, we do got about 100% there. Once again, if you don't have 100%, something is probably missing, some other piece of information to figure it out. So in this case, we do have it. So we could assume 100 grams. And in this particular case, that would make us 4364 grams of phosphorus, which we'll use the molar mass of phosphorus from the periodic table to convert it into moles. We'll do the same thing here for our oxygen, 56.36 grams of oxygen. We'll divide it by 16 grams per mole for our oxygen. That's going to get us here 1.4091 moles of phosphorus and 35225 moles of oxygen. In this case, it is going to be our phosphorus that is the smaller of the two. So we're going to divide everybody by the 1.4091. And that's going to give us a 1 there. And when we do it for our oxygen, we are going to get basically a 2.5 in this case. So clearly that's not good, as we can't have whoops, go back. We can't have a decimal there. So we have PO 2.5. Obviously, if we times that by 2, that's going to clear our guy into a whole number, which will then basically give us P2O5 as our empirical formula in this case. Now that we do have the empirical formula, we could get the molar mass of our empirical formula here, which would be 2 times 3097 plus 5 times 16. And that's going to get us here about 141.9. We're going to use that and the molar mass that was given to us in the problem here and divide the two. Again, larger guy up on top there. Going to give us basically a 2 in this case when you do that. That is what we're going to multiply this by to get our molecular formula, which will give us P4O10 in this case, which would be our molecular formula. Any questions on that one there? So again, on these problems, it's important to make sure, especially if you have percentages, that they do add up to 100. Also, if you're given something like, hey, you have a 6-gram sample and it's this many grams of this element and that many grams of this element, that those do add up to your sample size as well. Again, if not, something is missing. Now, if you have a problem like this, there isn't another approach that you could kind of take, which might be good if you'd like to do it. So if you do have sort of the percent composition by mass of each of the elements, and you have the molar mass of the compound, and you're looking to calculate the molecular formula, you could kind of use basically the definition of percent composition by mass, which means when we look at this number here, this compound is basically 43% or so phosphorus, which means out of that molar mass, 43% of it is made up of phosphorus. So you can convert the percentage into a decimal by dividing by 100 or moving the decimal place, whichever way you like to do that, our point. And if you times it by the grams from the molar mass here, that will basically give you how many grams of that is phosphorus, which in this case would be something like 123.89 grams of phosphorus. Could do the same thing for our oxygen. It's about 56% oxygen. So 0.5636 times our molar mass here. And that'll give us basically how many grams of it is oxygen in this case, which is basically the remaining part, about 160 grams. Now that you have it, you actually can divide it by the molar mass of each of these compounds or elements. which is our 3097 grams per mole, and our 16 grams per mole here of oxygen. That's going to give you a 4, and that's going to give you a 10 when you do that. And you could actually start by calculating the molecular formula here first by using the percent composition by mass. Then we know the molecular formula to the empirical formula is the simplest whole number ratio, which means you just figure out how you could reduce it down. Obviously, in this case, we could reduce it down by 2 and still hit whole numbers, which would give us our P2O5, which would then be our empirical formula. So if you do have the percent composition by mass given to you and the molar mass of that compound, you could actually start with the molecular formula first, using the percent composition, and then once you get the molecular formula, you basically could reduce it down to the empirical formula, kind of like we did earlier on in the chapter when we had molecular formulas. If you don't want to worry about that, clear, you could do what we did in the previous slide before we did this. You could just do it the other way as well, in each way. But you really do need sort of the percent composition of each of these things. So if you have some of the problems like we had earlier where they're just the grams, it's probably not worth taking the time to figure out the percent composition or anything like that. So I would just roll the other way and doing it, but this is an alternative way that you could do it. Any questions on how to calculate molecular formulas, empirical formulas? Okay. That should wrap up chapter 8 here. We're going to go back to chapter 6, I think. Give me 1 sec to find it. Actions. Really, this chapter is not too long of a chapter. It's just really about equations and balancing equations. Then chapter 7, we'll get into different types of reactions. And chapter 9, we'll do little calculations that involve equations. So how do we know a chemical reaction occurred? There are several signs that we could see that lets us know that a chemical reaction occurred. Remember that a chemical reaction is a chemical change. And the definition, right, of a chemical change is what you start with and what you end with are fundamentally different things, right? And you can't kind of get them back like we can with a physical change. So sometimes a color change indicates that a reaction has taken place. Some type of solid that forms that obviously wasn't there before you mix things together is an example of a reaction taking place. Bubbles being formed is usually an indication that you just made some type of gas, and clearly that wasn't bubbling before you did anything. So that's usually a pretty good evidence that a reaction is taking place. Also, heat and flame, either being produced or absorbed, is also a sign of a chemical change has occurred or a chemical reaction. Clearly, the flame you should be able to see. But heat, for example, you may also feel if you say you're holding on to a test tube, again, and the reaction is exothermic, that test tube should feel hot to you because it's releasing heat and energy into your hand, which is why your hand will start to feel hot. Also, if you're holding onto a test tube and it starts to feel cold to you, that would indicate that the reaction is a endothermic reaction, is absorbing energy, and your hand feels cold because it's sucking out all the energy from your hand. And now your hand kind of feels cold because it's losing all that heat and energy along the way. So these are all really signs that a chemical reaction has occurred. This is like the electrolysis of water, which you'll do pretty much not this, similar to this, except for dropping the 9-volt battery into the solution. But you basically can break apart water by running electrical current through it, and you can generate hydrogen gas and oxygen gas, and those are obviously all the bubbles that represent the gases that are being formed. Solid, bubbles, heat, all clues of a chemical reaction. This is sort of a titration type of situation. And here we can see some color change happening, which means usually some new products have been made that have a different color than what you started with originally. You'll do this one as well. You'll make a little lead 2 iodide, and they'll yell at you not to put the yellow in the trash can or anything like that, or make the lab all yellow when you're done. But basically, you pour 2 solutions together, and you'll make this solid, which obviously wasn't there previously, which would indicate that something new has been made and a chemical reaction is taking place. Obviously, some more bubbles here. In terms of a chemical reaction, as we'll talk about in a later chapter as well, there's really kind of 3 reasons why a chemical reaction occurs. sometimes referred to as the driving forces for a chemical reaction. Pretty much it involves electrons being transferred, so some type of transfer of electrons, some type of solid being formed, and the formation of water. Pretty much every reaction that we come across pretty much boils down to one of those three things happening. Electrons being transferred, solids being formed, or you made water. That's pretty much the deal on all reactions in most cases. When we get to chapter 7, when we talk about ways to classify it, we will see that that's pretty much what's happening in every reaction that occurs. And obviously that's our flame. So when we look at a chemical reaction, we oftentimes can display a chemical reaction as a chemical equation. And chemical equations are used to represent what is going on. And we want to, for example, a couple important things. When we do write an equation, we do represent everybody by their chemical formula. So here we have hydrogen gas reacts with oxygen gas to form water. We do want to always make sure when you have an equation that you start with the correct formulas. And that's a very common mistake that people make, especially if they're giving things in words, or if they're given just the reactants has to predict the products. You always want to do it in this order. You want to get the right formulas, and then you want to balance. And what happens when people try to do both together is a lot of times they will get the wrong formula. The thing will not balance the equation. And that oftentimes happens when you have kind of your starting material here, your reactants, and you're asked to kind of predict what goes on the product side. People try to write formulas and balance the equation at the same time. And that's never a good idea because you will probably get things incorrect. You also want to make sure, right, when we use something like hydrogen gas or oxygen gas, which are sometimes referred to as molecular hydrogen and molecular oxygen, that those are diatomic molecules and that you do use the twos, right? H2, N2, bless you, O2, all of our halogens as well, F2, Cl2, Br2. Again, otherwise you're going to have the wrong formulas. Things are not going to balance correctly. So in this case, we have H2 plus O2 gives us water. This is what is sometimes referred to as the unbalanced equation. And pretty much in chemistry, we never use an unbalanced equation. Pretty much everything that we do that involves an equation, it needs to be balanced. And so you never want to use an unbalanced equation. So as I mentioned before, this could be read as molecular hydrogen reacts with molecular oxygen to yield. And to yield is basically how you say it in words for the arrow part of it. Water, basically, in this case. So in this case, we know that this is an unbalanced equation, which we definitely would not want to use this way. And also really important, as we'll talk about here, when we do balance the equation, it is only the coefficients that we change, just the numbers that come in front. We never touch any of the subscripts because if we do, then we're changing really what that thing is, and we don't want to do that. As we'll see, if we just kind of keep track of what's going on the left-hand side of the arrow and the right-hand side of the arrow in terms of the elements, remember that the subscript goes to the guide to the left. So there's 2 hydrogens there, also 2 there. This is 2 oxygens and only 1 oxygen if there's nothing written. And we can see here in this case that it is the oxygen that's not balanced. So once again, we would want to balance it by only putting coefficients. So we would put a 2 here. And by the way, when you do put a coefficient in front, it does go for everybody behind. So you also have to kind of distribute it to each of the elements in the formula as well. And that would give us 4 hydrogens and 2 oxygens. And this is also a very common thing that happens when you balance an equation. You fix one thing in, screw up something else. So we could fix that by coming back over here for our 2. And that would give us 4 hydrogens and 2 oxygens in this case. So we should always use a balanced equation, should only change the coefficients in front. Again, never the little guys, and never weird things that people like to do, put big numbers between letters in the formula or something like that. So no weird things like that. So as we just talked about there, we can balance the equation. The reason really we do balance the equation is when we have a chemical reaction, it's all about electrons and bonds. So basically we break all these bonds and we make all these bonds. Because it only involves electrons, and as we know, basically protons are most important in terms of what element we're dealing with. Because we are only playing with electrons in chemical reactions, whatever elements you start with is the same number of elements you should have on the other side of the equation. They may just be in different compounds along the way. That's because hydrogen on the left there has a mass of like 1.008 grams per each. And on the right, it also has a mass of 1.008 grams, which means you should not lose any mass along the way because we don't change any elements along the way. So we do balance it again with the appropriate coefficient as we just did there a second ago. And now we get our balanced equation. And you should always make sure, as I mentioned earlier, that the equation is balanced. So if you come across an equation and you do not see any numbers there in the coefficients, you should definitely take a pretty hard look at it to make sure that it's balanced. And if it's not, you should balance it. I would say probably 9 times out of 10, if nobody's trying to trick you or anything like that, and you do see coefficients in an equation, it's probably balanced, but you should always check it as well just to double check. But I would say most of the time, you're probably going to be pretty safe on that if you do see some coefficients. When we look at the equation, everybody on the left-hand side here, these are our starting materials, which are reactants. These are the guys who are going to break all of those bonds, basically. They're going to reassemble on the right-hand side of the arrow, which are products, which are the stuff that are formed as a result of this chemical reaction. These are a few ways that we can interpret a chemical reaction. We're going to see more of this in chapter 9, but we could use the coefficients, for example, and say that for every 2 molecules of H2, it reacts with 1 molecule of O2 to give us 2 molecules of H2O. In chapter 9, this is pretty much going to be our guy right here, what is sometimes referred to as the mole-to-mole relationship, which is also just the coefficients. So we could also say that there are 2 moles of hydrogen react with 1 mole of oxygen to produce 2 moles of H2O. It's nothing more than really just a coefficient. This is our law of conservation of mass because all those elements on the left and right have the same mass. You should end up with really the same sort of molar mass of all the elements that are present as you go through a chemical reaction. There are other information that we do see in chemical equations. S for solid is sometimes written next to a formula, L for liquid, and G for gas. So all these guys are in the state of gases. We got a liquid there, gas, and a solid that's happening. We also will see the AQ symbol next to something, which means aqueous, means really a solution or a water sort of environment. Now, although most of the time we do use chemical equations to represent chemical reactions and chemical changes that are occurring, we can use a chemical equation to represent a physical process. And that's what we see down here. That is water in the liquid state going to water in the solid state. And that is freezing of water, which is a physical change that's occurring. This is water in the liquid state going to gas water there, or water in the gas state. Which is basically steam, also a physical change. So most of the time we do use our equations for chemical reactions and chemical changes, but you can use equations to represent physical changes that are occurring, which is what we have down here. Remember, a physical change is what you start with and what you end with is fundamentally still the same thing. It hasn't really fundamentally changed to anything new. Other things that we sometimes will see in equations, we'll see sometimes water written above the arrow, and that usually indicates that you're taking something and dissolving it in water. And again, a reminder that there is a difference between something in the liquid state and something in the aqueous state. Something in the liquid state is like a pure liquid, like water by itself, pure substance. But if you took a pure substance like water, and like what we see in the equation on the bottom, some solid sodium chloride would dissolve in the water and make a sodium chloride solution. which is basically a homogeneous mixture, right? Everything looks the same throughout, and it's a physical sort of change that's occurring in that particular case. So pure liquid, just one thing. Aqueous means basically it took at least two things and basically made a mixture of it, and it's a homogeneous type mixture. Other things that we also will sometimes see on top of the arrow is a catalyst. And a catalyst is not a reactant. It's not a product. It does not get used up in the reaction. Typically, a catalyst is there to speed up the chemical reaction. Now, there are catalysts that can slow it down, but most people, when they talk about a catalyst, is referring to it as speeding up a chemical reaction. So, for example, instead of just saying catalyst, you may see some metal written up there, like PT, like platinum. You may see H plus, which indicates that this is an acid being used as a catalyst. So, a lot of times you may see those things written up on the arrow. In addition, our triangle, that usually means heat is sort of being applied as well. The little triangle on top of the arrow as well. So sometimes equations will have a lot of information sort of going on there, the states of everybody in there, any type of catalyst or anything that's sort of also being added to the reaction is sometimes seen. Any questions on that there? So let's talk about some of the steps to go about balancing the equations. And I would say probably most people do a trial by error, lay down some numbers on one side, some numbers on the other side until things sort of work out. But here are some of the steps that you could follow if you like. The first one again is really important. As I said a little bit ago, you definitely want to always make sure that you're starting with the correct formulas, regardless of the balancing parts. So just keep that in your head. Correct formulas, then balance. Don't do those things at the same time. Once you have all the correct formulas down for everybody in the equation, then you should balance it. And once again, we balance it by changing only the coefficients. One approach is to start with the most complicated one and then kind of work your way around after that. Keep using coefficients until you have the same number of elements on both sides. If you successfully do this, there's really two things you need to make sure of when you have an equation that's properly balanced. You need to make sure that all of the whole numbers, all are whole numbers, the coefficients. So all the coefficients has to be whole numbers, and they do need to be the simplest sets of whole numbers. So what do I mean by that? Let's just say you balance an equation like 4a plus 6b goes to 8c, and this is all balanced with those coefficients. Now, although it may be balanced, you can still go through all those coefficients and you can reduce them down to whole numbers. In this case, by dividing by 2, everybody by 2. So if you can do that and still get whole numbers, you should, and the properly balanced equation should look something like this. And you need to just double check that your coefficients cannot be reduced down any further. Again, they still need to be whole numbers when you reduce them down to get the properly balanced equation. The reason this could happen is sometimes people will see larger numbers to balance the equation, and it is absolutely balanced, except that you do need to reduce down those coefficients. So sometimes people will see different numbers to balance equations. Here's another approach, which is beginning with coefficients where the elements on the same side of both equations. Also, formulas of these elements have the same coefficients. You then can look for elements that appear only on one side, and then finally make sure that you're balanced. So here's another approach if you want to look at it. That's really more practice, I think, will be good. So let's take a look at one here together. So if I have this equation, let me just show you how I would sort of go about it. I'm going to first just rewrite it so I have a little bit more room for my coefficients here. I personally do like to make tables just to kind of organizes things. It also gives you an idea as to where to start and where to go next, sometimes rather than just kind of throwing numbers out at the coefficients. So I would make a reactant side, a product side, and just kind of list my elements here. And I would just do a little counting. So I got one nitrogen there. I got two nitrogens there. I got one oxygen there, one oxygen there. And on the left-hand side here, I got two hydrogens there and two hydrogens there. So now I have this table. I could clearly see everybody looks good except for nitrogen. So frankly, that's a good place to start since that's the only one that's not balanced in this case. So we again could fix this by changing the coefficient. And we're going to put a 2 in front of our NO. Once again, this 2 does get distributed to everybody behind, which means that we now have 2 nitrogens. We would then have 2 oxygens and still 2 hydrogens. So this is very common. As I said earlier, you kind of fix one thing and screw up something else. But the table is helpful. We could also see now that really oxygen is the only thing that is not balanced. So that will tell me to go to the right-hand side and balance my oxygen. Once again, using a coefficient that will count for everybody behind it. And that's going to give me 2 nitrogens, 2 oxygens, and 4 hydrogens. So I'm getting closer in this case. I've now balanced the nitrogen and oxygen. I can clearly see from my table, the only one that's not balanced is hydrogen. And I can easily fix that now by going back to the left-hand side and putting a 2 there. And that's going to give me my 4 hydrogens, 2 oxygens, and 2 nitrogens in this case. So now I do have my sort of balanced equation. Any questions on that there? So I would recommend doing a table. You don't necessarily have to, but it can be very helpful when you're starting to balance equations. Just kind of keep things organized and gives you, again, like I said, sort of an organized place of where to attack, where to start, and sort of where to go. Any questions on that? All right, so why don't you try the next one here? See what Okay, so let's take a look. Once again, I'm going to make a little table here, reactant side, product side. Got carbons, hydrogens, and oxygens. On the left-hand side here, 3 carbons, 1 carbon there. We got 8 hydrogens. Over here, we got 2 hydrogens. Left-hand side, we have 2 oxygens. Right-hand side, we have 2 oxygens there, plus 1 more there, gives us a grand total of 3 in this case, right? And now we can see here, really nothing's balanced. So really from my table and just looking at it, probably the easiest thing to balance would be the carbon. So that's a good place to start. We could just simply put a 3 right there. Once again, that 3 is going to get distributed to everybody behind, which would give us 3 carbons. In terms of our hydrogen, we will still have 2. In terms of oxygen at this point, we now have 3 times 2, which is 6, plus 1 more over here, which means we're now up to 7 oxygens in this case. So we fix the carbons. We have hydrogen and oxygen still left to balance. I personally am going to choose to go with hydrogen first because frankly, it is the easiest because it's only in one place on each side. We have oxygen in a couple places on the right and one place on the left. So that's a lot of things where it's at on the right-hand side. So I'm going to start with just the hydrogen here first to balance, and that's going to be easy to do by putting a 4 here. That again going to get distributed to everybody behind. Will give me 3 carbons. 4 times 2 is 8 hydrogens. Now in terms of my oxygen, I got 3 times 2, which is 6. I have 4 times 1, which is 4. And that means I do now have a grand total of 10 oxygens in this case. That means that was much easier to fix now my oxygen by simply putting a 5 over here on the left-hand side. And that's going to give me 3 hydrogens, 8 hydrogens, 3 carbons, and 5 times 2 is 10 oxygens in this case. So sometimes it's best to leave the most complicated element for the end, especially when you got like an element in multiple places on one side and by itself on the other. Any questions on that there? All right, let's try another one here then. All right, right and okay, so again, you're not given the equation, although on your notes, I think you might be. We want to start with the correct formulas here. So diboron trioxide. Di means 2 borons, trioxide means 3. Reacts with water to make our boric acid. So once again, I'm not going to be concerned at all about the balancing. I just want to make sure I get down all the proper formulas first, and now I should balance. So I'm going to make my little table here. We got BOH, looks like. So we got 2 borons on the left. We have 1 on the right. We have 3 oxygens there, plus 1 more there makes 4. We on the right hand side, this 3 does get distributed to everybody in the parentheses. So we do have 3 oxygens, 2 hydrogens on the left, and also 3 hydrogens on the right. Not a lot to work with here, so might as well just start with the boron, which is up in front. To balance the boron here, we're going to put a 2 in front of it, which, by the way, gets distributed to everybody behind, including with the 3s. So that means that we have 2 borons. We have 3 times 1 for the oxygen, times 2 is 6. And same thing here for our hydrogen, we have 6 as well. So in this case, with that 2 in front, you got to multiply it by 3 and then multiply it by the 2 on the outside as well. So again, it counts for everybody like that. At this point, I'm not going to play with anything on the right-hand side because I got nothing left to do. So we do need to go to the left-hand side. Once again here, I'm going to start with the hydrogen because I see oxygen in multiple places on the left-hand side. So I'm going to kind of save that for the end. So here to fix the hydrogen, which seems a lot easier, I'm going to put a 3 there for my hydrogen. And that's going to give me 2 borons. In terms of oxygen, I have 3 there, and this 3 goes to that oxygen as well, which gives me 6, and 3 times 2 is 6. So in this case, by starting with the hydrogen, it actually fixed the oxygen as well, which oftentimes will happen as you're balancing an equation. Kind of everything will fall into place, hopefully, at the end, as you sort of put numbers in there. Any questions on that there? All right, let's try another one here. All right, balance this equation, see what you come up with. Okay, let's take a look and see how we're doing on this one. So we're going to make a table here, reactant product, a little nitrogen, hydrogen, oxygen. So we have 1 nitrogen on the left and 1 on the right. Not too bad. We got 3 hydrogens on the left, 2 on the right. Oxygens on the left are 2, and we have 2 on the right. So everything looks balanced except for the hydrogen, which seems like a good place to start. In this case, we actually need to put numbers on both sides to get a balance. Common number between 3 and 2 is 6. So to get my hydrogen on the right to 6, I need a 3. And to get my hydrogens to 6 there on the left, I will need a 2. That would then give me 2 nitrogens, 6 hydrogens, and 2 oxygens. On the right-hand side, 1 nitrogen, 6 hydrogens, and 4 oxygens, as I got 3 there and 1 more there as well. Next easiest thing to fix would definitely be the nitrogen, since it's only in 1 spot on each side, and I already have a 2 on that side, so I do need a 2 to lock in my nitrogen over here. And that's going to give me now 2 nitrogens, 6 hydrogens. And now in terms of oxygen, I'm up to 2 there and 3 there, which means I got 5 in this particular case. Any questions up to there? So clearly at this point, we should just go to the next problem. No, clearly at this point, we don't want to change any of the other numbers because there's nowhere else to go but the O2. So we essentially need to turn our 2 into a 5. And we could do that by perhaps using like a fraction, like 5/2, for example. If I use 5/2, that gives me 2 nitrogens, 6 hydrogens. And when I take 5/2 times 2, the 2's cancel, it gives me 5 oxygens in this case, right? It is balanced. Is it correctly balanced? Can I leave it as with a fraction? I cannot. So this is a good example that you can use a fraction to balance the equation. Sometimes you need to use a fraction to balance the equation, but you can't leave it as the fraction with your equation being properly balanced. So we can use it to balance it, but we do need to get rid of it. So to get rid of a fraction, I believe they say multiply by the denominator, which is that guy on the bottom. So we're going to multiply everybody by that denominator that's on the bottom, and that will get me 4NH3 plus 5O2 gives me 4NO plus 6H2O. And if I didn't screw it up, we should still be balanced. So we have 4 nitrogens on the left, 4 on the right. 4 times 3 is 12 hydrogens on the left. 6 times 2 is 12 on the right. And oxygens, 5 times 2 is 10. There's 4 oxygens there, plus 6 more is 10 right there. And we are balanced in this case. So this oftentimes happens when you have sort of the diatomic element molecule that's an element on one side, and you got that element in a couple places on the other side. It oftentimes will happen. How do you choose the proper fraction? It's pretty simple. Up on top is the number you need. So if you remember what we were just doing, we needed a 5, so that's what went up on top. And on the bottom should match the subscript, which is usually a 2. So this number should match that guy, and you'll always choose the right fraction without having to think about it. So number you need up on top, number on the bottom should match the subscript, and then just make sure that you clear it and do not leave the fraction. Otherwise, it would not be properly balanced. Yeah. So absolutely, you could use a fraction, just got to clear it. Any questions on that there? All right, we will lay it up there for today, I think.